Okay, atomic spectroscopy. So when atoms or molecules absorb energy, that energy is often released as light energy. It has to be released somehow. The visible light energy is something that we can see. This happens with fireworks, with neon lights, with fluorescent lights. If we take the light that's emitted from these molecules or atoms, what we see is not a continuous spectrum like we do from the sunlight with a solid rainbow. We see a unique pattern of lines of different colors, and it's called an emission spectrum because this is the light that has been emitted. It actually functions almost like the fingerprint of an element, and you can use it to identify elements. This phenomenon cannot be explained by classical physics, just like the photoelectric effect cannot be explained by classical physics. So here are photographs of some lamps. This is a mercury lamp, a helium lamp, and a hydrogen lamp. It's just an evacuated tube that has mercury vapor, helium vapor, or hydrogen gas in it, and then you put it into a box that applies a voltage and passes a current through it. So we're exciting the atoms or molecules in the lamp by putting energy into them, and then they absorb the energy, but then they release it back out. If we take the light from these lamps and pass it through a slit to narrow it down, and then pass it through a prism, it's separated by wavelength, just like the sunlight was, but instead of a continuous spectrum, a solid rainbow, we only see particular frequencies of light that are emitted. This, we can also see light emission in flame tests. You can take a piece of nichrome wire and dip it in sodium chloride solution and stick it in a flame. The Bunsen burner flame is this pale blue, and then this flame will be bright yellow because that's the energy being emitted from the sodium as visible light. Where did the energy come from? It came from the heat of the Bunsen burner. Potassium gives a purple light, lithium is a dark red, and barium's kind of hard to see. It's actually kind of a greenish color. But different colors depending on what the element is. And if you take the light emitted from flame tests and pass it through a prism, you're also going to see an emission spectrum. So this is the emission spectrum of helium, barium. This is white light, such as from the sun or from perhaps an incandescent light bulb. Here's oxygen and neon. And we see that the patterns of the lines are different. Which lines are present is different. The colors are going to line up. Well, they would if they were. These line up. But they're separated based on their wavelength. You can also observe an absorption spectrum. So you can shine light onto the metal or onto the vapor of the metal and observe what light is absorbed. So for mercury, this is the emission spectrum. We see bright lines where the light is emitted. The absorption spectrum is like a negative in photography. It's the opposite, and so we see dark lines where these particular wavelengths of light were absorbed. Any questions? Yes?
So primary colors and everything, I know what you're saying, like blue, indigo, violet, and all that kind of stuff, but is indigo just a combination of blue and red, and maybe the two different wavelengths combined at the right place to make a different wavelength?
Well, indigo is between blue and violet, and I've never been really clear on exactly what color indigo was, because it looks like just blue and violet to me. But when you mix like paints, you're mixing substances that you mix blue paint and red paint, right? The blue is reflecting the red light. No, sorry. The blue is reflecting the blue light. The red is reflecting the red light. And when you combine those together, they give the appearance of the violet or purple. So yeah, that whole idea is different than what we're talking about right here.
Okay, I got you. So the whole purpose of the emission spectra is aimed at identifying the element?
Well, just the existence of the emission spectra was very startling, and led to ideas of quantum mechanics, and led to new models of how the electrons are arranged in the orbitals. Because so far all we've talked about really is the plum pudding model, where you had this nucleus. No, that wasn't. We've talked about the nuclear model of the atom. So you've got a nucleus, and that's where all the positive charges are. And so far we haven't really said anything about what are the electrons doing. The emission spectra, particularly of hydrogen, led to the development of a model of the atom, describing what the electrons are doing. So they were looking at these spectra and trying to make sense of what they are. Johannes Rydberg took a more quantitative approach to this, and a numerical approach, if you will, and he looked at the atomic spectra and tried to find an equation that would describe the lines. And he came up with an equation, and it involves the inverse square of integers. And so he found that 1 over the wavelength of the line was equal to some constant times the quantity 1 over m squared minus 1 over n squared, where m and n are just integers. Could be 1 and 5 or 2 and 3, but we can describe the lines that occur based on that. So that's all very cool, but it doesn't explain anything. It doesn't explain why atomic spectra are discrete, why they have lines instead of a continuous spectrum. It doesn't explain why atoms are stable, doesn't even explain why the equation works. And we're going to do an experiment on Thursday where we're actually going to measure the wavelength of light from different element lamps, and we're going to calculate R, the Rydberg constant. So this is what we've talked about up until now in terms of the atom, Rutherford's nuclear model. So we've got this tiny dense nucleus with almost all the mass and all the positive charge, and then we've got the electrons doing something. Well, there's problems with that in terms of the electrons. Electrons are charged particles and they're moving. According to classical physics, a moving charged particle gives off energy. So if that's true, then the electrons should be constantly giving off energy. And then maybe atoms should glow. But at the very least, the electrons are continuously losing energy, so eventually they're just going to crash into the nucleus and the atom's going to collapse. And yet it doesn't. So obviously there's something lacking in that explanation. The nuclear model also doesn't explain what's going on when these atoms absorb energy and why they give off this light when they release the energy. What's going on with that? Well, Niels Bohr, Swedish scientist, developed a model explaining how the structure of the atom changes when it undergoes energy transitions. And the hydrogen spectrum was a big part of this. So his idea was that the energy of the atom is quantized, and that the amount of energy in the atom is related to the electron's position in the atom. And what quantized means is that there's only specific amounts allowed. It's a little bit like stairs. If you climb a set of stairs, you can be on the first step, you can be on the second step, on the third step. There are only certain positions allowed. You can't stand between two stairs. But on a ramp, it's continuous, and you could move up just a teeny tiny bit, or you could move up 2 giant steps. But on stairs, there's the individual stairs, and you can be on one or the other, but you can't be in between. That's something that's quantized. So Bohr's idea was that the energy of the atom is quantized. So in the Bohr model of the atom, the electrons travel in orbits around the nucleus. So the Bohr model is a lot like our idea of the solar system, where we have the sun, and then we have the planets orbiting around the sun, right? So the electrons are orbiting like planets around the nucleus, and they are at fixed distances in their orbits, and the energy of the orbit is fixed as well. And the energy of the orbit is going to be related to the distance from the nucleus. So he explains the emission spectrum this way, that electrons are going to emit radiation, emit light, when they jump from an orbit that has higher energy to an orbit that has lower energy. And because those orbits are quantized, there's only certain transitions that are possible, so there are only certain frequencies of light that are possible, and that explains the discrete wavelengths that we see. The emitted radiation is a photon of light. That photon has a frequency, and we can look at it and determine its frequency. The distance between the orbits determines the energy of the photon. If the distance is larger, the energy of the photon is greater. If the distance is smaller, the energy of the photon is smaller. The electron cannot be between states. It can be in one orbit or another, and it's never in between. Now, this is different than a person going up a set of stairs. Because when you go up the set of stairs, you're standing on one step, but then you're propelling your body and you're actually moving between one step and the other. Electrons jump. It's called a quantum leap. They're in one orbit, bang, they're in the other. They did not go in space in between them. And that's where the quantum mechanics stuff starts to come in. Like teleporting, or like, that old show, Quantum Leap, where the guy just instantly traveled from one place to another. That's quantum leap. Travel from one place to another without going anywhere in between. So the Bohr model is relatively easy to understand because we can kind of visualize it. Look at my shoes. My shoes have sort of a Bohr depiction of atoms on them. It's like the solar system, right? We can picture it. It has great historical and conceptual merit, but it's not correct. So let's look at this. So here's the idea of the Bohr model. Here's the nucleus, and this is not to scale. Here's the first orbit, the second, the third, the fourth. As you go out, they increase in energy. And so that violet line that we see for the emission spectrum of hydrogen, 434 nanometers. This is higher energy light than the red light. The difference in energy between energy level 5 and energy level 2 corresponds to this energy. And so by measuring the frequency of the light, we can actually measure the energy change that the electron underwent, and you can do all kinds of really neat calculations and calculate all kinds of stuff about the hydrogen atom. The problem is, it only works for hydrogen. So it doesn't work even for helium. It falls apart. It just doesn't work. None of the calculations work. So it's great and all, but it's not the ultimate.